Hello class, welcome to this video on the Unit 1 test review. So we're going to review on one version of the test. You could take notes on what we do and the reasoning for each of the questions and use this as a ticket to do the retake. Of course, you obviously won't have version A, you'll have a different version of the test. But here we go. So unit test. Unit 1, remember Unit 1 has 2 chapters in it. It's chapters 1 and 2. And so the first 10 questions are chapter 1 related. The second 10 questions are chapter 2 related. And then for the free response, we have one big question with parts that is chapter 1 related. And then the rest of the other 2 questions are chapter 2 related. Okay, so a little bit from each chapter. All right, so here we go. The first question, the pie chart on the right describes the distribution of state tree types for the 50 states in the United States. The category Other includes all trees that are the state tree for 2 or fewer states. Which of the following conclusions can we draw from this chart? All right, so it says, so let's look at part A. So we're looking for the one that is incorrect, or that is correct, that we can draw. A correct conclusion. So some states have not designated a state tree. That is incorrect because remember the ones that says other, it says other includes states that do have a state tree, but there's only 2 or fewer states that actually have that as their state tree. So that's what the other category is for. So A is incorrect, okay? B, the cottonwood is the state tree for 12 states. Is that true? Well, there's 50 states, they said, and cottonwood is 6%, so we got 6 out of 50, or I'm sorry, not 6 out of 50, 12 out of 50, if they said it's 12 states, so 12 out of 50 times 100, that's 24%. So it can't be 12, right? Because it's 24%, right? So and it says here clearly it's 6%. So it's actually not 12 states. It's actually a lot less than that. All right, so cannot be B, so we can eliminate that. So if I look at part C, taken together, oak, pine, and maple are the state trees. Also keep in mind that this other, I forgot to mention this, this includes all 50 states. That's what it says. It says the state tree types for all 50 states. Okay, so and then the other is just other types of trees. But if we go back to the taken together, oak, pine, and maple, right? Oak, pine, and right here, oak, pine, and maple. They're the state trees for more than half of the states. Is that true? Well, let's see. 20 plus 12 plus 10, right? 20 plus 12 plus 10. So that looks to be 42%. So that's less than half. So that can't be correct either, right? So it can't be A, B, or C. All right, so it says there are 10 states that have designated a pine as their state tree. So designated a pine tree. So let's look at that. Pine tree, that's 20%, right? So if we said 10 states, 10 out of 50 times 100, that's 20%. That is true. So we got 20%. Have designated pine. That is correct. Part E, there is no state that has designated the eastern red cedar as its state tree. Eastern red cedar. Well, we cannot conclude that from the chart, right? Because it's actually not given here. Now, it's possible that it's in the other category, right? But we can't necessarily conclude that. So we're going to eliminate that choice as well. All right, so let's look. The following bar graph gives the percent of owners of 3 brands of trucks that who are satisfied with their truck. From this graph, we may conclude the following. So owners of other brands of trucks are less satisfied than the owners of these 3 brands. Okay, so first off, remember that for this bar graph, this is only given us for these 3 brands. It's not giving us information about the other trucks. So there's no way we can determine whether that's true or not, whether the owners of the brands are less satisfied. Remember, this is saying that out of those who owned a Ford, less than 95% were satisfied, right? Whatever this is 96, 95. So, between 94 and 95% are satisfied. Now, this is saying out of those who own a Chevrolet, about 97% are satisfied and 3% are not satisfied, right? So this is what the data is saying. It's not saying, we can't really necessarily imply anything about other trucks and satisfaction for that. So Chevrolet owners are much more satisfied than Ford or Toyota owners. Okay, now at first glance, this looks to be the correct answer. However, remember that this is a tricky question. This is a Chapter 1 question. Chapter 1 question is testing misleading graphs. Now, this graph looks misleading because it looks like Chevrolet is way more than Toyota and way more than Ford. In fact, if I look at the Ford, it looks to be 1, 2, 3, maybe 4 or 5 times bigger than the Ford. And that is deceiving. And the reason why is because this does not start at 0. This starts around 94%. And so by starting at 94%, it exaggerates the difference here. These are actually minor differences. This is only a difference of 2%. So it's very little. So we cannot say that they're much more satisfied. We can only say that they're a little bit more satisfied when we compare them. It looks exaggerated, right? But that's because of the misleading graph here. There are only small differences in the satisfaction. This is correct. There's only small differences, only a difference of 2% or less. All right, so it might be a little bit more than 2%. Like here is 2.5% perhaps, and then this one's like but it's in a neighborhood of 2.5 to 3%. So it's really small. Part D, a Chevrolet probably sells more trucks than Ford or Toyota. Remember, this is not saying that there's more Chevrolet owners and therefore more trucks. This is just saying out of those people that have Chevrolets, what percent of those people are satisfied. So it's not saying anything about how many there are, right? A pie chart would have been a better choice for displaying this data. That is incorrect because if you look at the data, this is like 95, 96, 97. There's no way you can add up these percentages to get 100%, right? Because we're dealing with conditional frequencies, not we're dealing with conditional relative frequencies, not like regular relative frequencies, right? So no, we cannot do a pie chart. Would not have been a better choice. All right, so number 3. Here are the IQ test scores of 10 randomly chosen 5th grade students. So we got 10 scores. To make a stem plot of these scores, you would use as your stems. So what would we use as your stems? So in this case, for number 3, if we use 0 and 1. So look at the stems. So the leaves are going to be the rightmost digit. The stems are going to be in this case, 2 digits, right? Whatever is to the left of that. So in this case, the stems that you would want to use here, the smallest stem would be like 9, right? And then you'd have 10, 11, 12, and 13. You do not want to skip stems. So even though we may not have like a 12 stem or whatever, or a 10 stem. See here, the smallest stem is 9. Then we have an 11 stem for 110, 118. We have a 12 stem for like the 122 or 125. And we got a 13 stem because of the 130. And we got a 14 stem because of the 145. But we do not want to skip stems. So we do want to include the 10, even though there's no 10 stem. So the correct answer is B. Okay. All right, so number 4, if a distribution is skewed to the right, which of the following is true? All right, so if the distribution is skewed to the right, that means it looks like this, right? Something like that, where you have the longer tail is to the right. Now, if the longer tail is to the right, remember that the median is usually where most of the data is at. So the median might be like around here or something like that, right? Let's just say that that's where the median is. It's approximately the 50% point. Meaning like 50% of the graph is here and 50% of the graph is there, right? The area under there. So it might be like roughly here or something like that, where that's 50% to the right, 50% to the left. Now, when we look at this, when we look at the distribution that's skewed to the right, that means the mean is going to be pulled in the right direction. So that means that the mean might be like here, right? To the right of it. If it's skewed left, the mean is going to be pulled to the left. If it's symmetric, the mean and the median are the exact same, right? So if we have a symmetric curve, the mean is equal to the median, right? So the median is equal to the mean. X bar is your mean. You can also say mu, right? Or we can say mu if we're talking about population. But in any case, the mean is greater than the median when we have a skew to the right curve. So it cannot be B. The mean must be less than the median. No, that's not true. That's for skewed left. The mean must be greater than the median, so it's got to be C. Okay. All right, number 5, rainwater was collected in water collectors at 30 different sites near an industrial complex, and the amount of acidity or pH level was measured. The data range from 2.6 to 6.3 pH. The following stem plot of the data was constructed. All right, so which of the following box plots is a correct representation of the same distribution? All right, so first off, in order to do the box plot, we need to find the quartiles, the minimum, all that stuff, right? So the minimum is 26. We can see that right there. So the minimum is 26. We need our quartiles, Q1, Q2, Q3, and then we need our maximum. Our maximum is pretty easy to spot. That's 6 and 3, so that's 63, or 6.3, I'm sorry. According to the key, 3/7 is 3.7. It'd be kind of odd to have a pH of 63, considering that the pH is usually, up to like 12, 13, 12, maybe 14, something like that. Okay, so minimum is, so 6.3. The highest would be like 14 pH, so the 6.3 is like in the middle, or, almost in the middle. We got minimum is 2.6. And it says that right here, actually. I just realized that. But first quartile, we have, let's do the median. So the median is the second quartile. So where's the middle of the data at? So if we look at the middle, we have, so let's cross these out. So we got 1, 2, and just work our way towards the middle. 1, 2, 1, 2, 1, 2, 1, 2, so on and so forth. We're going to zoom in on that. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, almost there. 2. Okay, so here we have two middle numbers of 4.4 and 4.6. So we got to add those up, divide by 2. So we got 4.4 plus 4.6 divided by 2. So that's 8. So that's going to be 9 divided by 2. That's 4.5. Halfway between that. That makes sense. 4.5. And then, so now we got our median, which is between those, which means it's going to split the data into the left half and the right half. So let's do the first quartile, the middle of the left part. So 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, and so on. All right. Okay, let me double check again. So, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, yeah, so it could be 1, 2. We gotta include that. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. It's gotta be one middle number, so it's gotta be 3.8. That's my median. Okay, I wanted to double check that because I knew something was off. All right, so now we got 1, 2. We gotta include that 6. 1, 2, work our way towards the middle. All right, so that's 5/6, so that's 5.6. All right, so we just got to pick the dot plot that graphs that. So we got 2.6 here, that's around there. 3.8, so we're looking for 3.8. That can't be A because that's less than 3.5. That looks about 3.8. 4.5 for the median. That looks exactly 4.5. And then 5.6. Yeah, it looks like 5.6. And then 6.3. Okay, so the answer's got to be B. B is the best. All right, number 6. A sample of 250 high school students were asked if you had $1,000 to contribute to one kind of charitable organization, which type of organization would you choose? Below is a two-way table of responses to this question and gender. Okay, so we got a two-way table. Which of the following conclusions seems to be supported by the data? Okay, so let's look at the first part. Most of the females who chose a health organization would have chosen an environmental organization as their second choice had they been asked. Okay, so part A, you can't determine, there's we don't have any information on that. So like here it says, okay, out of the, so it says most of the females who chose a health organization would have chosen an environmental organization. We don't know that. Out of these 50 females, do we know whether they would have chosen environment or an international aid? We have no idea. Their data does not, we don't have any data to support that. We can only go based off of the data that we have. So we cannot assume that based off of the data that we collected. There's no association between gender and choice of organization. Okay, is there an association between your gender and what you choose? Well, let's take a look at health for female versus for male. So in other words, if I'm a certain gender, am I more likely to choose one or the other? So let's take a look at that. Okay, so let's go and take a look. So in order to do this, we need to figure out, well, how many males are there, how many females are there, right, in total? So we're going to see, okay, there's 50 females that chose health. So let's look at female and health, right? Let's just do the conditional probabilities for female and health and male and health. So we're not doing the entire conditional distribution. We're just doing part of it. So let's look at health. So if we look at health, there's 50 females that chose health out of how many? How many females were there in total? So it says, okay, so let's go ahead and add that. So there's 19, 33, 50. There's 28, and then there's 10. So there's 140 females, which means that there should be 110 males, right? Because there's 250 students that were asked. All right, so 110, and then 28 were male that said health. Okay, so let's compare those. We can see that those are different. Let's compare those. That's 35.7% compared to males. That's 25.45%. There's a difference here. If you're female, you're more likely to choose health. In fact, 10% more likely, right, than males here, if you look at it. They're more likely to choose health than they are, than male, right? So if you're female, you're more likely to choose, you're 10% more likely to choose health. Okay, so here there's no association. That's incorrect. There is an association. We see that gender does play a role in what they choose, right? And you can compare that to the rest of them. It has that same kind of pattern. All right, so the proportion of males who said they would contribute to an environmental organization was higher than the proportion of females who said they would contribute such an organization. Okay, so let's look at that. At first glance, you look at the numbers and you're like, well, no, there's 29 males, so that's less than the number of females that endorsed or would chose an organization. However, they're asking for the proportion, the percent. They're not asking for the frequency or amount. There's less males that chose environment, but out of how many, right? So there was 29 males out of 110 versus 33 females out of 140. So you see the difference there? So it might be that there's less males, but there's a greater percentage or proportion. Here there's 26.36% for males, and then for females is 23%. Okay, so females 23, male is 26%. So a greater proportion of males chose environmental. All right, so that's got to be C. All right. Okay, here we go. So number 7, a small company that prints custom t-shirts has 6 employees, one of whom is the owner and manager. Suppose the owner makes $120K per year and the other employees make between $40K and $50K per year. One day, the owner decides to give himself a $30,000 raise. Which of the following describes how the company's mean and median salaries would change? Okay, so in other words, we're introducing an outlier. So now the owner decides to give himself a $30,000 raise, which means we introduce an outlier. So now the owner changes from 120 to 150,000, right? So what happens to the average? Well, the average is obviously going to increase, right? How much is it going to increase though? Well, we added, we know that the average, well, we can calculate the average. That's not too difficult to do. So we got 1, 2, 3. So if you think about it, there's 6 employees, right? So if I add an extra 30,000, then 30,000 divided by 6, if I average that out, that's going to actually increase my average by 5,000. Okay. So if I introduce that increase of 30,000 divided by 6 people, then that's a $5,000 increase overall. So the mean would increase by $5,000. However, what happens to the median? Well, because the owner obviously is the outlier, and it's on the left end of this, is on the right end of the spectrum, 150,000. So let's say we had 120,000 and we had 5 other numbers here. Is that going to really change the middle number? No. If I increase this and I change that to 1 million, that's still not going to increase my median. My median is still going to be in the middle. So no change to the median, but $5,000 increase to the mean. So its answer's got to be B. All right, so let's take a look at number 8. The mean speed of vehicles in the cars only lane of the New Jersey Turnpike is 68 miles per hour. The mean speed of vehicles in the any vehicle lane is 64 miles per hour. What must be true about the mean speed of all vehicles on the turnpike, assuming that these are the only types of lanes? All right, part A, it could be, it says it could be any number between 64 and 68 miles per hour. Is that true? Well, the answer is yes, it could be, that's true. We have some that are 64, we have some that are 68. So basically this is a weighted average, right? This is saying, okay, we got 68 miles per hour for X amount of vehicles. Let's say, we'll just say W1, where W is the weight of the vehicles, like what percentage of the vehicles are traveling at 68 miles per hour. Plus, we have the 64 miles per hour times the weight of that. So what percentage of vehicles are traveling at 64 miles per hour, right? That's essentially what we're doing. Or what decimal, I guess, if you will, whatever, over W1 plus W2. Okay, so percentage, or let's do it as a decimal. So for example, let's say 0.5 of the vehicles, or 50%, same thing, right? 0.5 of the vehicles are traveling at 68 miles per hour. 0.5 of the vehicles are traveling 64 miles per hour. So let's do that. We got 0.5. 0.5, so 50% on both, right? And 0.5 plus 0.5 is just 1, right? So it's just going to be 68 times 0.5 and 64 times 0.5. Now, if I do that, then that's going to be 66 miles per hour, because that's half of them are 68, half of them are 64. Well, what's halfway between 68 and 64? 66, right? You can do the math. Now, if there's more people that travel 68 miles per hour, then obviously this is going to increase, right? This number is going to increase from 66 to like 66.5, 67, so on and so forth. And if this number increases, right, this percentage increases for 64 miles per hour, then this 66 miles per hour is going to decrease, right? And that's how it works. So in other words, the smallest that it could be is 64 miles per hour. The largest is 68, is somewhere in between, right? So it says it must be larger than the median speed. That's not necessarily true unless, it says it must be larger than the median. We actually can't determine that. The median is at the 50% mark, right? So if these are, and it might be 66, depending on how many there are, right? So we actually can't determine that because we don't know how many how many traveled at each speed. It must be larger than 66. Again, we don't know how many traveled, right? If it was larger than 66, then there might be more than 50% here, but we don't know that information. They don't tell us. It must be 66 miles per hour. That's incorrect because, again, we don't know that it's 50% on each side, right? We only know how many. We don't even know how many. And so the answer has to be A. It has to be between 64 and 68, depending on what percentage are in each lane. All right, so number 9, the mean birth weight of infants born at a certain hospital in the month of April was 128 ounces with a standard deviation of 10.2 ounces. Which of the following is the correct interpretation of the standard deviation? All right, so remember the standard deviation, the formula for the standard deviation is S equals the square root of the sum of the deviations squared, meaning how far each data point is from the mean. X bar is the mean. Let's just use, X bar is the mean, squared. So how far is the data from the mean squared divided by n minus 1. So essentially, this is an average. This is essentially an average. Okay, an average of what? An average of how far the data is from the mean. That stands for the mean. Okay, so how far is the data from the mean? That's the interpretation of standard deviation. So how far is the data from the mean on average? So all the infants born weighed between 117.8 and 138.2 ounces. No, that's not what the standard deviation tells you. About half of the infants weighed between, no, that's incorrect. It's not saying half of them were between a certain weight. That would be the median, right? The median, or like the interquartile range, rather. The interquartile range gives you like, it's between this and this, right? Like about half of them. No, so this is incorrect. We're not talking about percentages or anything like that. The difference between the mean weight and the median weight of infants was 10.2 ounces. Again, that's the difference between the mean weight and the median weight. No, that's incorrect. The distance between the weight of each infant and the mean weight was on average about 10.2. That is correct. The distance between the weight and the mean weight was on average about 10.2. That is the correct interpretation. All right, so number 10, a medical researcher collects health data on many women in each of several countries. One of the variables measured for each woman in the study is her weight in pounds. The following list gives the 5-number summary for the weights of adult women in one of the countries. So country A, we got 5 adult women, we got their weights. About what percent of country A women weigh between 110 and 240 pounds? Okay, so this is the 5-number summary right here. The following gives us a 5-number summary. So not for 5 adult women, sorry. I think I said 5 adult women. I meant to say 5-number summary. So the 5-number summary for those women. So remember, the 5-number summary, this is the minimum, first quartile, median, third quartile, and the maximum, right? That's what it's given us. Now, in the box plot or in a 5-number summary, this is worth, from here to here is 25%. From here to here is another 25%. Here to here is another 25%. And from here to here is another 25%, for a total of 100. Okay, so here it's saying between what percentage are between 110 and 240. So between here and here. Well, if I count that, from here to here is 25, 25, 25. That's a total of 75%. So 75 between those two. Okay, so the answer is C. All right, that's all there's to it. It's just it's knowing how to deal with box plots and 5-number summaries. All right, so 11. The heights of American men aged 18 to 24 are approximately normally distributed with a mean of 68 inches. So now we're officially in chapter 2 territory. So now we're going from 11 to 20 is chapter 2. 1 through 10 is chapter 1, right? So now here, number 11 is chapter 2 territory, which we can see that we are dealing with normal distributions. All right, so approximately normally distributed with a mean of 68 inches. So we got a mean of 68 inches, mu is 68. And a standard deviation, that's our sigma, lowercase sigma, is 2.5. Only about 5% of men have heights outside the range of, and then we have to choose. So this is tricky wording. So first off, it says only about 5% of young men have weights outside. That means that 95% have heights inside. Okay? So we're looking for 95% for whichever one of these. Okay? So if we can find whichever answer has 95% of men, then that's our answer, right? It's the same thing as saying 5% outside of that range. So that's something to keep in mind. All right, so that was tricky, that wording there, that word outside. Okay, so 95%, which is the same thing as 0.95, right? And it's a approximately normal distribution. Well, if you think about it, what does 95% sound like? If you remember the empirical rule, that was the 68, 95, 99.7% rule, right? And that says that if I have a normal distribution, then about 1 standard deviation away, right? If I'm 1 standard deviation away on either side, that's 68%. If I'm 2 standard deviations away, 1, 2, then that's 95% of the curve. Sorry for the drawing, the crude drawing here. And if I'm 3 standard deviations away, I'm 99.7%. So in other words, what we're going to do is I'm going to redraw this, and I'm going to say, okay, how many are 2 standard deviations away? Okay, so here it says the mean is 68, so we're going to draw a normal distribution with, this is 68, the mean is in the middle, the standard deviation is 2.5, right? So that means we're going to add 2.5 to and subtract it. So add it to the right side, that's 70.5. 68 minus 2.5 is 65.5, right? And then minus another 2.5, that's 63.0, and then another one is 60.5, and then I'm going to keep adding 2.5 now, so it's going to be 73.0, and then 75.5. So this is 1 standard deviation away, this is 2, and so on and so forth, right? Okay, so from here to here should be 68%. From here to here is 95%. That means we're looking from between 63 and 73. And the answer is B. All right, 95% of men are between 63 and 73, which means 5% are outside that range. All right. Okay, so let's look at the next question. So use the information in the previous problem about what percentage of the men are over 70.5 inches tall. All right, so 70.5. So what percent are above it? Well, let's recall what the percentages are. And I can actually use the same. Yeah, I'll just do another one. Okay, so this is the mean. This is 1 standard deviation, 2 standard deviations, and 3 standard deviations, okay? I'm just going to put 1 sigma, 2 sigma, 3 sigma, just so I don't have to write all this stuff out, okay? Okay, so this is 6, and then I'll cut this in the middle. So from here to here is 68%, which means each of these are 34, right? Percent. From here to here is... yeah, from here to here is 95, which means each of these guys has to be 68 minus 95, so 95 minus 68, 27 divided by 2, because we got to cut it in half. So each of these are 13.5. Okay, and then finally from here to here is 99.7. Did I write that rule down? Yeah, it was 68, 95, 99.7% rule, which means that each of these, this has to be 2.35. Let me double check that. So 99.7 minus 95%, and then 4.7 divided by 2, so that's 2.35% there, and then 2.35% here, which means each of these has to be 0.15%. How do I know that? Well, because the whole thing is 100%. 100% minus 99.7 is 0.3, and then 0.3 divided by 2 is 0.15%. Okay? And now we want it to be greater than, right? So we're going from 1 standard deviation, 2 standard deviations, 3 standard deviations. So we're actually going beyond 1. Okay, so that means we're going here to there, right? And so that means I had to add these percentages up. 13.5 plus 2.35 plus 0.15. So if I add that up, I get 16%. All right, so what percent of young men are over 70.5 inches tall? The answer is 16%. The answer is C. All right, number 13. Now you can get these percentages real quick if you just remember that, the empirical rule, and just remember these numbers. These numbers will never change for the empirical rule, so you might as well dedicate them to memory to save some time. All right, number 13, for the density curve shown to the right, which statement is true? All right, so this is a density curve, and we want to figure out what is true about it. Okay, so the area under the curve is between 0 and 1 is 1. Is that true? Is the area under the curve between 0 and 1 1? Well, it says it's a density curve, So we know that a density curve by default has to have an area of 1, right? And it is between 0 and 1, right? So so we're saying that the area here has to be 1. Well, that's the entire curve, right? So the entire curve has to have an area of 1. So that's true. The density curve is symmetric. No, it's not symmetric. Skewed to the right. No, it's not skewed to the right. It's normal? Nope. None of the above. Okay, so it has to be A, because by definition, if it's a density curve, the area of the curve underneath there has to be 1. Number 14, for the density curve shown in the previous question, which statement is true? The mean and median are equal. The mean is greater than the median. The mean is less than the median. The mean could be either greater than or less than the median, or none of the above. Okay, so let's take a look at that. Well, remember that the median is the 50% mark. So we're 50% of the curve. If we have 50% of the area to the left, 50% of the area to the right. Okay, that's what the median is saying. All right, so first off, if you look at this density curve, it's definitely not symmetric, right? Because if it were symmetric, the mean and the median would be both equal to each other. All right, so that eliminates D. Cannot be, or sorry, C. It cannot be I'm sorry, which one says that they're the same? A. The mean and the median are not equal, right? If you look at this curve, it looks to be, skewed in one direction. It looks to be skewed to the left, right? There's a long tail here, skewed to the left. So that means that wherever the median is going to be the 50% mark. The median is going to be probably somewhere around here, where this is about the same area as that. Okay, approximately. It's not. It might be more here. It's whatever value divides it so that this is the same area as that, right? That's what we want. We want this to be 0.50. We want this to be 0.50. That's what determines where the median is at, right? Now, the mean, however, is going to be pulled in the left direction because we got a long tail on the left side, right? We got some outlier stuff going on here, right? And stuff going on the left. And therefore, we would expect that the mean would be pulled in that direction. And so the mean might be somewhere here, perhaps, I don't know, wherever it is. It's going to be pulled to the left. And so we know that the mean is going to be less than the median. All right, in a future lesson, we'll look at the formula for calculating the mean of a probability distribution or probability density, but we won't be looking at it for the cases like this. Like this curve, in order to find the mean of this probability density curve, first off, you need to know the formula for the function of this curve. You need to know the function, what the function is, whether it's f of x equals x squared, whatever. And you also need to be able to calculate the integral, right, underneath this curve, right? So we won't be doing anything like that. However, you just have to know that because there's, it's the x bar is based off of the x values. If you got some really low x values, that's going to make the curve go to the left, right? So that's going to make it skewed, or the curve is skewed, so it's going to pull it to the left. All right, so that's what you got to understand for that. Number 15, the area under the standard normal curve corresponding to z being between negative 0.3 and 1.6 is what? This one is literally just looking up on your table. So look up in your table, the between negative 0.3 and 1.6. So you have to actually look up the table, look up two values of z, right? So look up the value for z is negative 0.3, look at the value for z is 1.6, and then subtract them, okay? Now keep in mind that the area shown in the table, right, this table, it shows you to the left, all right? And so what you got to do is you got to look up the 1.6, look up the negative 0.3, and then subtract them. So in other words, the probability or the area where z is between those two values is equal to the probability that z is less than 1.6 minus the probability that z is greater than, or that z is less than negative 0.3. So this is the value from the table. The table gives you the area to the left. This is pointing to the left, right? So the table gives the area to the left. So this is the probability that z is less than a certain value, okay? So we just got to look it up and then subtract them. All right, so let's look at 1.6. Positives are on this side. So we got 1.60, 1.60. So that's got to be 0.9452. So we'll write that over here, 0.9452. And we got negative 1.30, negative 0.30. So negative 0.30. It's got to be this guy, 0.3821. So we just got to subtract those and get our answer. All right, 0.5631. So that answer is C. All right, number 16, the graph at right is a normal probability plot for the amount of rainfall in acre feet obtained from 26 randomly selected clouds that were seeded with silver oxide. So they seeded them with silver oxide and then they measured the amount of rainfall. Which of the following statements about the shape of the rainfall distribution is true? All right, distribution is normal. Is that true? This is an interesting question that it's good to understand that it actually doesn't talk about this in the book per se. It doesn't actually talk about it in detail. Last time I checked, I might actually have mentioned it. In fact, I believe it might have mentioned it once, but it wasn't in the slide. It wasn't like shown in detail. But when you're doing a graph of the z-score versus the x in this case is the rainfall, z-score versus the variable, if you graph the z-score versus the variable and the function is normally distributed, so this is let's say x is the rainfall, right? If I graph the z-score of this, like I convert it to z-scores, and I graph that where I have z and x, then I should attain a line that is approximately straight, so a linear. Okay, every time I graph z-score versus x, it should give me a straight line. That is something that I didn't go over in too much detail, but it's something that I want to make you aware of, because this is a question that I asked on the test. But remember, this question, this comes from the book, and the book did make quick mention of this. All right, so which of the following statements is true? Distribution is not normal because this is not a straight line, right? It's not approximately normal, again, because it's not a straight line. Skewed left, skewed right, distribution has no potential outlier. Okay, so I'll go over in a little bit of detail here. So like we said, if it's approximately normal, you should see a straight line. If it's skewed to the right, so if I have something that is skewed to the right, then when I start drawing the z versus x, what that's going to do is that this is the linear, but it's not going to be a line. It's going to actually, you're going to have higher z-scores here, right? These are the high z-scores, and these are the low z-scores, correct? On the left side. Well, you're going to have less of the low ones, and you're going to have more you're going to have more high. So what's going to happen is that as you proceed, this is actually increasing in z-score faster. So what's going to happen is it's going to look like this. It's going to have this kind of curvy nature to that. All right, so that's how it's going to look like if it's skewed to the right. All right, if it's skewed to the left, okay, so it's going to look kind of like that. So the data might have this curve that goes above it. Now, if it's skewed to the left, then what's going to happen, so if you got a curve that's skewed to the left like this, right, that's skewed left, then when I do this, this is the ideal, it's going to bend below it. So because remember, if it's bending below it, that means you have lower z-scores. And if you see that, you have some low z-scores here, right? Those are affecting those low z-scores are affecting your result, right? And so you're going to have something that might look that will kind of bend like that, okay? So you'll have a curvy nature like that. And of course, if it's in the middle, that means it's normal. So, and this is if it's skewed to the left, right? So I did want to make mention of this. I didn't go over this in detail, but I want to make sure that it was technically in the book, it made quick mention of it, saying that if it's linear, it's normal. I think there was one example where if it curved like this, they said it was skewed to the right, but it was so it was so quick that you might have missed it if you didn't look at the book carefully. but I did want to mention it. So now you know what it is, so that way if you see that type of question, you can answer it easily. So the answer is it's skewed to the right. It's got to be E because this is the linear, it's doing that bend above it. So that's skewed to the right. All right, 17, the distribution of the time it takes for different people to solve a certain crossword puzzle is strongly skewed to the right with a mean of 30 minutes and a standard deviation of 15 minutes. The distribution of z-scores for those times is, okay, so it says it's strongly skewed to the right. So when we look at this, so remember that this is a transformation question, right? So this is a question that's dealing with transformation. So what happens to the shape if I transform it? Remember, to calculate the z-score, I got to take the value minus the mean, right? Divided by the standard deviation. So when I do a subtraction transformation, that does not change the shape at all. What it does is it just changes the mean by that amount, right? Each of the values gets changed by that amount, including the mean. But it doesn't, yeah. So that would just change the mean. It wouldn't affect the shape or anything like that. If I divide by a certain number, I take each of the numbers and I divide by a number, that's not going to affect the shape. That's just going to affect the spread, right? So these are things that you're going to want to know, right? Like what gets affected by what transformation. Okay, so in this case, what's going to happen is that each of the numbers is going to be subtracted by the mean and divided by the standard deviation. But when I do that, that's going to make the mean go to 0, right? And the standard deviation go to 1. The reason being that, if I transform anything to a z-score, we always start with 0 as the mean, and then the standard deviation goes by 1s, right? Anytime we convert to a z-score, whether it's normal or not, we have the mean being 0 and then it goes by 1s. However, if the original is skewed to the right or to the left, then that shape is going to be maintained. That shape will not change, okay? This is from your notes. So in your notes it says if you got a transformation where you're subtracting or adding or dividing or multiplying, it's not going to change the shape. So that means that the shape is still going to be strongly skewed to the right, but the mean is going to be 0, the standard deviation is going to be 1. Okay, so let's review real quick. If I subtract a number, if I subtract the same number from all the data values, the mean is going to change by that amount. Okay, so if I subtract mu, then the mean is going to change. The mean is going to be x minus mu, right? The new mean, okay, the new one. All right, the spread is not going to change. The standard deviation is still going to be sigma, okay? So sigma is still going to be sigma, but it's not going to change at all. All right, so let me just put the new standard deviation is still going to be sigma. All right, and I should probably call this x the mean, because the mean is going to be mu, right? So mu minus mu is 0. Okay, so the new mean is going to be 0. Okay, so the original mean is mu. I subtracted mu from all the values, and so my new mean is going to be mu minus mu is 0. If I divide, so this is subtraction, if I divide by sigma, what's going to happen is that the new mean is not going to be affected. It's gonna affect the mean, right? So it's gonna change the mean by sigma, right? By multiplying by sigma, or dividing by sigma. Sorry. So okay, so the new mean is gonna be the 0, which was the mu minus mu, divided by sigma. But 0 divided by sigma is 0. So the mu mean is still gonna be 0. Now the new standard deviation is gonna be the original standard deviation, which is sigma, divided by the standard deviation here. The spread changes if you divide by number. So sigma divided by sigma is 1. Okay, so this is how we get that the scores or the values are going to be 0 and 1. Okay, so again, the mean is going to be 0, the standard deviation is going to be 1 because of these transformations. Now the shape is going to stay the same. So it's got to be skewed to the right with a mean of 0 and a standard deviation 1. So the answer has to be D. Again, go back and review transformations. That was chapter 2, lesson 1. If you need a refresher on that. Okay, so number 18, the cumulative relative frequency graph at the right shows the distribution of lengths of fingerlings at a fish hatchery. The interquartile range for this distribution is approximately what? Okay, so this is cumulative relative frequency. So that's like percent, and the percents are building up. So remember, this ogive, this is another word for this is an ogive, is giving you the percent, it's essentially a percentile graph. It's giving you like a percentile, right? So now interquartile range. Now interquartile range, remember, is Q3 minus Q1. The third quartile minus the first quartile. Now the third quartile is the 75th percentile. The first quartile is the 25th percentile. So you have to figure out, okay, where the 25th percentile is, where does the 75th percentile is, and then subtract them, okay? So here, the 75th percentile is approximately here. This is around 75%, which is around here. And so this is, it's about maybe 6.5 or so. So I'm just going to estimate it. So that's going to be approximately the third quartile. We'll just say it's about 6.5. Minus, now we got to figure out where the first quartile is. So we got to go about the 35%, the 25% rather. So that's around here. So that's about 5.5. So yeah, it's about 6.5 minus 5.5, which if I subtract those, I get about 1.0 centimeters. And the closest answer to that is 1.2 centimeters. So the answer has to be D, okay? So that's how you find the interquartile range, okay? And I guess we were estimating, but we picked the best answer. All right, so number 19, which of the following properties is true for all normal density curves? 1, they are symmetric. Yes, normal curves are symmetric. The curve reaches its peak at the mean. Yes, this is the mean. It's also known as the median, or it's also the same value as the median. And then 95% of the area under the curve is within 1 standard deviation of the mean. No, that's incorrect. That should say 2 standard deviations, right? So this is true, right? So these are both true. So the answer here has to be C, 1 and 2. Remember, this will be 2 standard deviations for 95%. 1 standard deviation is 68%. All right, 20. A fire department in a rural county reports that its response time to fires is approximately normally distributed with a mean of 22 and a standard deviation of 11.9. Approximately what proportion of their response times is over 30 minutes? Okay, so here we're saying we got a mean of 22 minutes and it's normally distributed. So we got 22 here. We got 11.9, so that's going to be 33.9. So on and so forth, right? But here we want it to be over 30 minutes. So 30 minutes is like around here. And we want it to be over 30 minutes, so it's got to be the area to the right. So what we got to do is we got to convert this to a z-score. So we're gonna convert this to a z-score now. We can't use the empirical rule because this is a number. This is not one of those nice numbers, right? So we're going to just kind of get the z-score. So convert it to a z-score, which is x minus mu divided by sigma. It says the mean is 22. That's my mu. And this is my x is 30. Okay, so we got x is 30. We got the mu is 22. We got the sigma is 11.9. That's my lowercase sigma. All right, so 30 minus 22 divided by 11.9. So let's convert that to a z-score. So that's going to be, so put parentheses around it when you're doing this on the calculator. So we have 0.6723. So about 0.67 is my z-score. Now we're going to look this up on the table. So 0.67. Let's go over here. We got to go to the positive side. The positive side is down here. Okay. So 0.67, 0.67. So we got to figure out where they cross. That's right here, 0.7486. 0.7486. Now that's the area to the left, not to the right. Okay, so 0.7486. So we got to be careful with that. So this is 0.7486. Now to get to the area to the right, I got to do 1 minus that. Okay, 1 minus 0.7486. Okay, so I'm going to put that in for my answer. So the probability that that x is greater than 30 is equal to 1 minus that is 0.2514. It's about 25%, or 0.25. So the answer is C. Okay, all right, that takes care of the multiple choice. So now we're looking at the free response questions. So for number 21, we all know that the body temperature of a healthy person is 98.6 degrees Fahrenheit. In reality, the actual body temperature of individuals varies. Here are dot plots and summary statistics of the body temperatures for 90 healthy individuals, 45 males and 45 females. All right, so we got the dot plots here. We got the and we got the summary statistics. So determine if there are any outliers in each distribution and show your work. All right, so this is where we got to do the work to do the for the outliers. Now remember, to do the outliers, you got to use the 1.5 IQR rule. I'll write it over here just so you have the formula. The low outlier is less than the first quartile minus 1.5 IQR. The high outlier has to be greater than the third quartile plus 1.5 times the IQR. So first off, we got to find the IQR and the quartiles. Here they actually give it to you. So they give you the quartiles and you can find the IQR. So you can find the IQR by subtracting. So let's do this for females first. So female, let's calculate the IQR. So the IQR, so first of all, let's write down what we know. The first quartile is 97.9. The third quartile is 98, or 0.8, yeah, for females. The IQR is the third quartile minus the first quartile. So if we do that, we get 0.9 for my IQR. And then we're going to do the low outlier and high outliers, right? So low outlier is less than first quartile minus 1.5 times the IQR. And we can do that in math over here. Just do that just because I'm, all right, just to make this easier. So we get 96.55. Oops. Okay, so let me just delete that. All right, so now let's do the high outlier. So the high outlier is greater than the third quartile plus 1.5 IQR. Right, so let's do that here. 98.5 plus 1.5 times 0.9. 99.85. Let me double check the IQR just to be on the safe side. Okay, good. So 99.85, a calculator. All right, now in this case, if you look, it has to be less than 96.55 or greater than 99.85 for it to be an outlier. If we look at the female data, we have one that's 100. We have one that's 99. Oops, I put 98.5 here. Sorry, let's just say 98.8. So let me recalculate that. So 98.8. Sorry, the highest one is 98.8. You can see right here, or not? Yeah, the third quartile. I don't know why I put 98.5 on that. Let's go over here. 98.8 plus 1.5 times 0.9. Okay, so that's 100.15. All right. Okay, so are there any numbers greater than 100.15? No, because the maximum is 100, right? So no high outliers. So no high outliers for females. Are there any low outliers for females? Well, there's the minimum for females. If we look at the minimum here, it's 96.4. That's less than 95.55. Yeah, and that's about it because the next lowest one is past 96.5. So that's this has got to be, so that's got to be an outlier there, and that's got to be an outlier there, or no outliers there. Sorry, just have the low outlier. Okay, so we have looks like 96. If I look at the minimum, 96.4 is a low outlier since that is less than 96.55. Okay, and then for males, we do repeat the same process. So Q1 males is 97.6. Q3 is 98.6. IQR. Subtract those, you get 1.0 or just 1. I'm just going to say 1 for that. And then we have the low outlier is less than the first. I need to rewrite this a little bit better. Less than 97.6 minus 1.5 times 1, which is 96.1. And then the high outlier is greater than the third plus 1.5 IQR, which is 100.1. Okay, so are there any numbers less than 96.1? Well, if I look at the minimum for males, the minimum for males is 96.3, which is above 96.1, right? So no minimums. So no minimum or no low outliers. And the high outliers, the maximum is 99.5, so that's not greater than that. So no high outliers. So males have no outliers. Females have one outlier, a low outlier. All right. So you get 1 point for the correct answer. You get 2 points, or another point for showing the your work for the outliers. Okay. Draw parallel box plots of these two distributions. Be sure to label the plots and provide a scale. All right, so here, if you want, you can use the same scale as here. You might as well use the same scale if you want. They start at 96, and then they go by 0.5s. So we can do that. All right, so let's go ahead and go by that same scale. And 9.0 all the way to 100. Okay, so we'll go up to 100. All right. Okay, so we want to let's do the female on top and male on the bottom, just like they have it here. All right, so we got the minimum for females is 96.4. So 96.4, that's got to be close to 96.5, right? So it's got to be like around here. So we're going to do females and male. All right, so we got 96.4 around here. We got the first quartile for females, 97.9. So it's close to 98. We got, and we have, the female is a low outlier. So this should be a star. So I'm going to put a star on this one because we said that 96.4 is a low outlier. So we got to put a star there. And for the next lowest number for the female is right here at 96. So it looks like 96.7. Right, that's what looks to be that number. That looks to be 96.7. So that's going to be around here, 96.7, right there. And then and then we got for our second quartile, the median, we said is 98.4. It's around here. Again, where you place it has to make sense based on the data for it to be fully correct. 98.8. It's going to be like around here. All right, and then we got our maximum, which was 100. So it's got to be right here. And then we can draw our box with our whisker. All right, so that's for female. And we're going to do the same thing for male. The males have no outliers, so we don't have to worry about the asterisks. So the minimum for male is 96.3, close to 96.4, just below that. Maybe like around here. Then we got our first quartile for males is 97.6, just above this. We got our second quartile median for males, 98.1. Again, it's got to be below this line for it to make any sense. 98.1 is around there. We got our third quartile, 98.6. It's going to be right here, just above that. And then our maximum for males is 99.5. Okay, so there is our parallel box plots for male and female. You could write like this, or you could use do like an axis there and call female male. That's fine, however way you want to do that. Write a few sentences comparing body temperatures of healthy males and females. So again, this is dealing with temperatures, so it makes sense for us to obviously compare body temperatures. All right, so when we compare, we got to use SOCs, right? So remember to compare using SOCs. Shape, outliers, center, and spread. So we're going to talk about each of those things. If you want, you can write them out, SOCS if you want. You don't have to, but it's a good, it's good practice. You can practice doing the SOCs. Okay, so when you talk about the shape, you could you can get a point for saying that the distributions are both approximately symmetric. So if you said that would be correct based off of the box plot. Again, when you're doing the SOCs, it's following from part B, right? So they're saying write a few sentences after you do this, which means you're probably going to be using the box plot when you're doing the shape, outliers, and stuff like that. Now, you could use this, but remember, they don't have to give you the dot plot for this. They could just give you the data points, right? They could say, oh, it's 96, 97. They can give you the actual numbers and not give you the dot plot. So when you're talking about the shape, you don't have to use the dot plot. You're given the parallel box plots for a reason, so use it. Now here you could say, okay, well, this is kind of roughly symmetric. You could say that. You could say that this is also roughly symmetric as well, right? That's also evident in the box plot as well. So if you look at the box plot, there is some rough symmetry there. This tail is a little bit longer, but overall it's approximately the same. If you said it was skewed to the left for males, that would be okay as well, because again, there's a little bit of this tail is a little bit longer, but not by much, but it is a little bit. So I'm going to say that they're approximately roughly symmetric. Okay, so both distributions are roughly symmetric. So you can use the dot plot, you can use the box plot combinations of those. Both distributions are roughly symmetric. And so that's S, right? And then O for outliers. Now we also have to talk, context, right? So we also want to make context. So both distributions. So let's. I'm going to do a little bit of context. Okay, so male and female body temperatures. Okay, just to include context there. Outliers. So there's one outlier, the distribution of female body temperatures. The distribution of female body temperatures has an outlier. So we'll go ahead and put that, has a low outlier of, and then the, what was that temperature? It was 96.4 degrees, right? So 96.4 degrees Fahrenheit. Okay, again, context, units, things like that. Center, the distribution of, or we could say we could talk about the females. So for the females, if you look at the center for females, the center for, let's look at the median. So the median for females, or you could say the median or average, right? Either way is fine. But since we're using the box plot, we can look at median. So the median for females is greater than the median for males. And so it was 98.4 versus 98.1, okay? Okay, so I'm going to say females typically have a slightly higher body temperature than males. And the males were 98.1, I believe. Was it 98.1? Yeah. All right, and then the S is the spread. So to talk about the spread, both distributions have similar variability or spread. You could say spread or variability. We can talk about the IQRs. The IQR for females is 0.9. IQR for males is 1.0. So they were pretty similar variability. All right, and there you go. So that's your SOX for that. Again, use the box plot to help you. I mean, some of you guys might have used a dot plot and use everything at your disposal, but definitely use the box plot and make reference to it at some point. All right, so number 22. Now this is a chapter 2 question. Here, 22 and 23 are chapter 2 questions. So it says a local post office weighs outgoing mail, finds that the weights of first class letters is approximately normally distributed, with a mean of 0.69 ounces and a standard deviation of 0.19. So that's your mu, that's your sigma. What is the 60th percentile of first class weights? So the formula, so if it says 60th percentile, that's saying that, okay, you got a normal distribution. We're looking for the X value, which corresponds to the 60th percentile, right? Where 60% of people are below, right? 60% means 0.6000, all right? So we need to convert this to a z-score, right? We need to figure out, okay, what z-score does this correspond to? So if we convert this to z, what z-score would that be for this to be 0.6000, okay? So in order to do that, we need to we need to use the z-table for this, okay? So we're looking for an area of 0.600 to the left, okay? So the left has to be 0.6000, right? That's what we're looking for, and then we're finding the z-score from that, which means that the area here has to be 0.6000. So what's the closest thing to that? Well, this is 0.5987, 6026. 0.5987 is closer. That's the closest to 0.6000. All right, so that's 0.25. So z-score is approximately 0.25. All right, so that means that the z-score has to be around 0.25. All right, so let's go back here. Z-score is 0.25. All right, that means our formula, remember our formula is z equals x minus mean divided by standard deviation. We got the z-score is 0.25. Our x value we don't know because that's what we're trying to look for. X is the question mark, right? Mean is 0.69, sigma is 0.16, and we're solving for x. Okay, so we got, in order to solve for x, we got to multiply both sides by 0.16. All right, and so so we got 0.16. Yeah, so let's figure out what 0.16 times 0.25 is. We could just do that here. 25, oops, 0.04. 0.04 equals x minus 0.69. Add 0.69 to both sides. So x equals 0.73. X equals 0.73 ounces. Okay, so the 60th percentile of first class letter weights is 0.73 ounces. All right, okay, so part B, the first class letter weights weighing more than 1 ounce require additional postage. What proportion of first class letters require additional postage? Okay, so what proportion weigh more than 1 ounce? Okay, so again, if it weighs more than 1 ounce, let's convert that to a z-score. All right, so z equals, now this is my x value, that's my x, is 1 ounce, right? So we got 1 minus the mean of 0.69 divided by the standard deviation of 0.16. Okay, let's convert that to a z-score real quick. Again, when you do this at once, put this in parentheses if you want to do it at the same time, if you want to calculate it. So here we got a z-score of 1.94, so 1.94 to 2 decimals. And we want it to be weighs more than 1 ounce, okay? So when we have the bell curve, and this is 1.94 ounces, or z is 1.94, we want it to be more than that, right? So greater. So that means we got to find the area to the left, subtract it from 1. Okay, so let's look at 1.94 on our z table. 1.9012, 1.94. That's 1.94, 0.9738. Remember, that gives us the area to the left. So to find the area to the right, we got to do 1 minus that, okay? So 9738, this is 0.9738. So we got to do 1 minus 0.9738 is 0.0262. Okay. So what proportion of first class letters at this place require additional additional postage? You get 0.0262 letters. So proportion of that many require additional postage. You could convert this to a decimal if you want. So 2.62%. Okay, so about 2.62% of first class letters weigh more than 1 ounce. All right, okay, that takes care of that one. 23, old-fashioned mechanical alarm clocks were not very accurate when the alarm went off. The density curve below describes the distribution of times a certain alarm clock went off. The scale on the x-axis represents when the alarm went off in seconds before negative or after positive the alarm was set to go off. What proportion of the time did the alarm go off within 10 seconds of the time it was set for? Shade the appropriate area. Okay, so you get a couple points for shading the correct area, and it's got to make sense, right? So if this is 30, 10, 20, 30, it's got to be appropriately divided. So this is 10, again, 10, 20, 30, so that's negative 10. So it's got to be appropriately divided. So you would have to shade this area right here. It says within 10 seconds. Within 10 seconds means it could be 10 seconds after or 10 seconds before, right? Within that time frame. Okay, so this is the correct area shaded. I'll do it in red just to emphasize that. That's the correct area. And then you get points for the work and then the answer. So it says the area of this, it says shaded, it says what proportion of the time. So the red proportion represents, so the area for this guy is, so you got to calculate the area. So we don't know what this height is. We just know that it's, if what you did is you calculated the percentage of that, then that would be correct. All right, so we can say the percent. So what percent of the graph is that? Well, you can clearly see that this is 1/3 of the graph, right? So you could say that the proportion is 0.33. Okay, the shaded area is 1/3 of the density curve of the area under the density curve. So the proportion is 0.33 or 33%. Okay, or you could say 1/3. If you want, so you could do that, and that would be sufficient. That would be, you can get full points for that, because that's specifying your reasoning and then your answer. You could also say, okay, this is x, and this is 20, right? Because 10 from -10 to 10 is 20. So the area under the red is 20x. The area, the total area is from 30 to 30, which is 60, and it's 60 times x, right? The area is 60x, is base times height because it's a rectangle. And so these cancel, leaving you with 20 over 60, which is 1/3, okay? All right, so that you can also, either one of those would suffice, and that would actually show, what they want, okay? With the work and all that. All right, thank you guys. I hope you found this lesson, or this informative, and that you learned something from this. And as usual, I'll see you in the next one.